Now we're going to put to work the main equation of quantum mechanics, the Schrödinger equation, and use it to solve a very interesting problem that will also illustrate why quantum mechanical effects are not important in our everyday life, while being essential when we're dealing with atomic length scales. The question that we're going to ask is what happens if we enforce a particle-like solution in our quantum mechanical problem. So basically what it means is that let's postulate that at t equals 0, at an initial moment of time t equals 0, we have the wave function such as this, which is called Gaussian wave packet. And this wave function basically describes a particle which is localized in space around 0. So it's a typical Gaussian around 0. And the spread out of this Gaussian is of order d, which is the parameter of the model. So a here is some coefficient. It's not very important at this stage. Now, the calculation that we are going to present is essentially the evolution of this initial condition with time under the action of the Schrödinger equation. And it's a bit technical question. So for those of you who are not interested in technical details, I would like just to present the final answer so that you can understand the bottom line without going into technicalities. And so the final answer is here. So here we have the wave function as a function of time, modulus of its squared, so which describes essentially the density of particles. And as we will see, this psi squared has the same Gaussian form as the original wave function. But the difference here is that the parameter d, which describes its spreading, it increases with time. And it increases with time as 1 plus t squared over some tau squared, where tau squared is this typical time scale at which the spreading occurs. So if we now look at this dependence of psi squared on x, as time goes by, we will see a more and more uniform density. So eventually it will be almost flat. Now, this basically implies that a particle-like solution, this type of wave packet, is unstable in quantum mechanics. So, but the important thing is the time scale itself at which this spreading occurs. And let us estimate this time scale for two sort of diametrically opposite cases. So one case will be the case of an electron, a microscopic elementary particle with a mass about 10 to minus 27 grams. And let's assume that it's localized on atomic length scales of order 1 angstrom, 10 to minus 8 centimeters. So if we plug in the numbers, what we're going to see is the typical time scale at which the spreading, the localization radius, if you want, of this electron doubles is of the order of 10 minus 16th seconds, which is an extremely short time scale, hardly observable in any experiment. Now, if we take on the contrary a macroscopic object, let's say a typical human being, which is also described by laws of quantum mechanics, so the difference will be quite noticeable. So here, well, the mass, of course, of a macroscopic object here will be around, let's say, 50 kilograms, and let's say we want to be localized on a distance of order 1 centimeter. Now, if we now plug in the numbers into this equation, what we're going to see is that the typical time scale at which sort of quantum delocalization of a human being occurs is of order 10 to plus 30 seconds. So to put this number in perspective, so this is equal to 10 to the 23 years, or 10 to the 13, 10 trillion lifetimes of the universe. So basically, it's a, in some sense, meaningless number. So it's a number which is never relevant in any realistic circumstances. So we shouldn't be worrying too much about being quantum delocalized due to quantum mechanical effects. And if you now look at different time scales for various objects that we're dealing in our everyday lives, we're going to see that essentially for all these objects, even the smallest ones, we can safely say that quantum mechanical effects are completely irrelevant. But the moment we're going to go to fundamental microscopic length scales is going to change very significantly. Now I'm going to actually derive the main result that I presented in the previous slide, the time evolution of the Gaussian wave packet. And as I mentioned to you, this derivation is a bit on the technical side. So those of you who are not really interested in these technicalities may just skip it towards the end of the lecture. But those who want to actually learn the technical part of quantum mechanics, which is the main part of quantum mechanics, should pay attention and perhaps rederive it on your own. Now, the main element of the solution is the decomposition of the the initial condition of this wave packet into the plane waves. So plane waves are presented here. So sort of as a motivation as to why we want to do something like this, we should recall that the Schrödinger equation was deduced or derived almost by construction to describe waves rather than particles. So the initial condition that we have chosen is in some sense an arbitrary function. So there's absolutely no reason why it would be a convenient solution to anything. So while the plane waves are indeed these solutions, and so by decomposing this function or any initial condition for this matter into these plane waves, we actually simplify things a lot, as we will see later. From the mathematical point of view, this decomposition is nothing but the Fourier transform of this Gaussian wave function into the harmonic functions, into this cosines and sines. And we know very well how to do this decomposition, but before we go to it, so I would like to remind you the following identity for a Gaussian integral, which actually we're going to use at least 3 times in this derivation in different contexts. So if we have an exponential of a quadratic function with some coefficients alpha and beta here, so the integral from -infinity to +infinity is well known, and it's given by this equation. So we're going to just use it later on. Now, the reason it's relevant at this stage of the derivation is because the Fourier transform, or in other words, these Fourier harmonics, which in the context of quantum mechanics are called wave function in the momentum space, are determined exactly by this type of a Gaussian integral. Because what we have to do in order to determine this phi of p, we have to evaluate the integral of this exponential e to the power minus x squared or 2d squared with this e to the power minus I over h bar px. And if we look at this integral, so and compare it with this Gaussian expression, we will see that alpha here is equal to 1 over 2 d squared, and beta is equal to minus I h bar p. So if we use now this formula, so beta squared is equal to minus p squared over h squared, and divided by 4 alpha will give us the following expression. So I completely ignore the overall coefficient, it's not really important for the following. So now let me just erase this and get rid of this Gaussian integral. So now we're going to interpret actually this Fourier transform in an interesting way. So the reason we have constructed this initial condition in this form was because we wanted to localize our particle sort of on a certain length scales of order d. So the uncertainty of our initial condition in the real space is of order d. But by looking at this sort of wave function in the momentum space, we see that the uncertainty in momentum delta p is of order h bar over d. So it's inverse proportional to the localization distance in real space. And so this sort of dual relation, so the more it's localized in real space, the less is localized in momentum space, is vice versa, is a particular manifestation of what is known as a general Heisenberg uncertainty principle, which is written here. So that in general, whatever wave function you have, whatever quantum state you possibly can construct, there is always a constraint that the uncertainty in position times the uncertainty in momentum is larger or equal than h bar being the Planck constant. So now we're in the position to solve the main technical problem that we formulated in the beginning of this segment. That is to solve the Schrödinger equation, the free Schrödinger equation here. So Hamiltonian here is just p squared over 2m, with the initial condition written as so. So instead of writing it as a Gaussian in real space, we write it as a linear combination of plane waves. That was basically the Fourier transform in the previous slide. Now, in order to write the time-dependent wave function, we need to take into account 2 simple circumstances. The first circumstance is the fact that the Schrödinger equation, the time-dependent Schrödinger equation, is a linear equation, which implies that if we have several solutions to this equation, psi1, psi2, psi3, etc., their sum is also a solution, with the initial condition being simply the sum of the corresponding initial conditions. Now, the second circumstance is we have to recall that a plane wave written as so is indeed the solution to the Schrödinger equation. In some sense, we have constructed Schrödinger equation such that it would give us this guy as a solution. And here the epsilon of p is the energy of the electron, the energy of the free electron, and it's simply equal to p squared over 2m. Now, if we take a look at the initial condition again written in this form, we see that it's an integral over momenta. But integral is a sum in some sense. It just happens to be an infinite sum. So we can use the fact that Schrödinger equation is a linear equation and write psi of x and t, the full solution, as so. So basically all we have to do is to replace this plane wave at t equals 0 with the plane wave at a finite time with epsilon of p being p squared over 2m. And so to write now the wave function in a more convenient way, so what remains now is to calculate the Gaussian integral over momenta. And it can be done again using the same identity that we used in the previous slide, but now the parameter alpha here is going to be d squared over 2h squared plus I t divided by 2m h bar, and the parameter beta now is I x over h bar. So again, if we use the same identity, what we get is the following expression for the wave function. We see that this expression is intrinsically complex function, but if we're interested just in determining the density of our particle, so where the particle is located, so the only thing which matters, as I mentioned already, and we'll discuss it in more details a little later, is the absolute value of the wave function squared. So this absolute value squared can be calculated. Again, we don't worry too much about the overall coefficients. We only look at what appears in the exponential. So we can write this density as an exponential, basically from here, minus x squared over t squared. But there is also another term, which is 1 over 1 plus t squared, or tau squared. And tau here is exactly the time scale we discussed in the beginning, which is mass times the localization length in some sense, d squared divided by h bar. So this completes the derivation of the main result that we discussed earlier, and also it completes the first lecture. Thank you very much, and I will see you in class later in the week.